Okay, we'll take a look at this furnace for checking the carbon content. You see, this is just an ordinary induction coil. You put the stuff in there, heat it up to about 2600 degrees with oxygen, and it will burn, and then you can proceed. Now, on the resistance high temperature furnace, which is another one that's used, you have carbide or molybdensilicide elements. Then the accelerators are used. You have a catalyst in it, and then you can detect the separated gases by one of the two detection systems that we had previously mentioned that provide a specific and consistent signal, and process it electronically. It's a lot of electronic stuff, but you can come up with an answer. On the infrared detection, you can apply it on the basis that various gases can absorb energy within a specific wavelength of the infrared spectrum. Now, this is similar to a scanning electron microscope analysis when you analyze something and you actually have a wavelength for a given element so that you can determine how much of each one you have in it. Then on the thermal conductive detection system, it's based on the principle that each gas has a distinct capability of carrying heat from the body. So you can take the carbon dioxide and determine the thermal conductive change generated by it and come up with the amount of carbon that was extracted. And in any sense, you can determine then the total amount of carbon that was in the sample and get an accurate reading on it. Now let's go to thread inspection, and this one is something that people talk about a lot, but it's kind of like politics. They talk about it a lot, but it's not a lot done. So I found out when I went to checking into it. The common methods of inspection that are given once again in this mill handbook H28 and are the systems 21, 22, and 23. They're also covered in ANSI B1.3M. Now, in general, the system 21 requires the least amount of inspection. System 22 is an intermediate amount, and 23 is the most stringent. And so each one of these is practically a separate document, so I'll just try to summarize them a little bit. But one of the things we found out is that most people just use System 21. And on System 21, all you're doing is checking the OD or ID and using a go-no-go gauge. Anyway, some of the things that you are looking for on threads, now this was up earlier in the course, but nevertheless, just to go through it again to familiarize ourselves with it. Here is the pitch of the threads, the distance between threads. Here is that angle, which is usually this alpha 1, alpha 2. The sum of those normally is 60 degrees on threads. Here is your vanish cone where you run out your threads. And here is the major diameter, which is the outside crest of the threads. The minor diameter, which is from the diameter at the root. And then the pitch diameter, which is a very important thing, and that's, of course, where if you mated the threads up perfectly, you would have the same thickness through the cross-section of the thread as you do in here, as you do in the mating thread here. And here's another one that I wanted to show you for this reason. This is kind of a close-up that shows the difference between having an unradiused thread and having a radius thread. The other thing is this circle here represents the pins that are used for measuring the pitch diameter. There's a method called the 3-pin method that they can put the pins 2 on one side, 1 on the other side, put flat plates across, measure it, then you go to a table, and you can find out from this table, based on the size thread you're using, the diameter of these pins, you can come up with an accurate reading of the pitch diameter of the thread. Now, for external threads, System 21 just includes go, no-go diameter and the major diameter. That's all that they do, and you can either measure this, you usually measure it with what they call a ring gauge, which is nothing more than a calibrated thread in a ring that to replace what you would normally use as a nut, and you try to thread the fastener into it. If it goes, it's fine. You turn use the other one, the no-go, and if it doesn't go in that one, that means you are within the acceptable limits. It doesn't tell you exactly what your dimensions are, but it just tells you that the thing will work. So that's called the functional diameter, if you will. System 22 includes the System 21 measurements plus pitch diameter. You can either measure it with a pitch micrometer, which is a micrometer that has a grooved head on one end of it that fits over a thread. Then you have a pin type on the other one that fits in a thread, and you can span this across the OD of the threaded area and get a reading which will give you the actual diameter, pitch diameter that you want, and you can look on a table then and see whether it's within the tolerances that you want. The thread groove diameter, which is the measurement between threads at the pitch diameter point. The functional diameter, which you get from up here with a go, no-go gauge. Lead and flank angles, and that's just go, no-go. Minor diameter, and then you can measure the root profile. But I found that that is not done that much unless somebody insists that it's done. System 23 includes all the others, plus now you get into the roundness of the pitch cylinder itself, the taper of it. In other words, if you take the whole thing as a cylinder, do you have taper on it? Is it round or is it lopsided? The cumulative thread form variation, going through the thing and checking to see whether it varies any from one end to the other. The lead and helix angle variation, the flank angle variation on the threads, run out, and even surface texture. Now, surface texture on the threads usually is not a problem, but you could measure it and see. It would only be if the thing had been coated with some sort of a coating that was not electronically or electrically deposited. In other words, if you had galvanized threads, then you could have a problem because you'd have extra plating material in the threads. And after you've gone through all of these things, this is just for threads. Nothing's been done on the rest of the fastener. So you could have a huge crack in it and it wouldn't make any difference because if you passed everything else, the guy say, well, I inspected the threads and they're good. So you still have to look to see if there's anything else wrong. Now for internal threads, you have the go, no-go, and the minor diameter. And that's about all that's usually checked. The go, no-go gauge, one end fits, the other one doesn't. And then with the minor diameter, you use a regular plug to slip in to check to see if it is okay. Then you move to the System 22. It includes the 21, and then you go for minimum material pitch diameter or thread groove diameter and the angles on the threads. But since this is internal thread, this is hard to do, so usually people don't do it. Now here's a go, no-go gauge. One side will thread in if it's in normal tolerance, the other side won't. And this is used to check internal threaded or tapped holes. And that's the only, usually that's about the only acceptance that people use, I found. Here is the go, no-go pin for just checking the minimum diameter in a threaded hole to see if it is within tolerances. And so this one is fine, and this one's not supposed to go. It is bigger than the tolerance bandwidth would allow the hole to be. Then for the system 23, it includes the others plus the roundness of the pitch cylinder and the taper of the pitch cylinder. And but still nothing on the internal thread radius. Regardless of what you call out, it's not measured unless you would go in and tell somebody you have to have it, and then as I mentioned earlier, using this dental plaster type stuff, you can actually cast it and then take it and put it on an optical comparator to see whether you have the radius that you want. So now we move on and to the cold hard facts of life, that even though you've inspected the heck out of the threads with these three systems, if you run it through all of them, you still haven't looked for manufacturing defects. For defects in the threads, FFS86 federal spec gives examples of acceptable and unacceptable defects, and we'll look at those in subsequent figures. And you will note that the acceptance of the thread defects becomes more critical as the fastener strength increases and the ductility decreases. So there has to be some engineering judgment exercised on it. Now, here's one of the things. Thread should have no laps or seams at the root or the flanks of the, here's the root, here's the flank of the thread. And so in general, what you're saying on this is any defects below the pitch diameter, because you're loading this part of the thread a lot more than you are this part. So anything below the pitch diameter in the way of a defect, a noticeable defect, you're not going to accept. When you get things above the pitch diameter, or outboard of it, here, now you can accept more defects there because it is more lightly loaded. But even so, there are limits on how much you can accept on it. So, once again, you look at it, and if you find too many cracks in a fastener, you really should reject it. Now, here's something that is a lesser problem. This looks bad. Having little nicks or something like that, as long as it's not a crack, if it's just a nick from handling, and it doesn't affect the functioning of the threads, you could probably accept a nick on the outside surface of the threads. Now, here is another method of thread inspection, a laser inspection method. Now, most manufacturing facilities would not have this at all because it is a setup with a full computer printout availability, and I think it costs about $100,000. So you wouldn't find them in your normal inspection shop. But it is a very accurate method of checking threads. It uses laser triangulation sensors and a motion sensor to digitize the thread form, and it's a non-contact method. You're using a laser beam. And the measurements are made by comparing the data obtained by laser scanning the thread to a perfect mating part that has been mathematically created in software. And the thread axis is the method you use for spinning it around so you can check it at different points. Now, these machines, though, are used for inspection equipment, because they're accurate enough. For instance, you can use them to inspect the thread plug gauges, go, no-go gauges, dies and taps. And they can handle parts up to 6 inches in diameter and 4 to 64 threads per inch. Now, it's a time-consuming thing, so the places that you would use it, say you don't have very many bolts holding an engine on a plane. So on a 747, if you wanted to inspect the super high-strength alloy steel bolts that are holding it on, you would run them through an inspection procedure like this, check every one of them, because there it's a super critical application. On the figure 78 is a picture of this one. You set the fastener down on the head. You can turn it. You scan the thread in because this is on a rotary spindle here. And once you scan it, then the table will index to another location. Then you get a thread profile that you can compare to a perfect thread. So if you're really doing something critical, this will work. In fact, I believe Marshall, I think, got one of these machines because they wanted to use it for checking some of the supercritical flight hardware for shuttle and installations that they were putting together there. So I went and looked at them. There's a company here in Westlake, I believe, handles them. And they do work well, except that you would not inspect something that was just an ordinary production part because it's too time-consuming, too expensive. Now, there have been various discussions through the years on how variation in pitch diameter on a fastener can do them in. And I guess this argument's been going on for 30 or 40 years or something like that. So the Industrial Fasteners Institute here in Cleveland initiated a research effort in 1993 to manufacture, measure, and test a bunch of fasteners that were deliberately made out of tolerance on pitch diameter just to see how bad it was. And they put out an article on that in Mechanical Engineering in the December 1996 edition. And the conclusion was that variations in pitch diameter don't have a very big effect on the joint strength, fatigue life, and clamping performance. In other words, it can be out of tolerance quite a bit and still pass the standard tensile and proof load requirements, which kind of surprised a lot of people. I thought it would have more effect than that because varying the pitch diameter, of course, you are loading your threads unevenly. But evidently what happens is that though you are loading them unevenly, you're spreading the load around to where you get more yielding, and it'll still carry the load. So some of the people who did the testing were surprised that it was that good. Now, moving to the other parts of the fastener, the head and shank inspection. There's one of the places where you can really get into trouble with a fastener is having any kind of a defect in the fillet radius under the head, because since that is one of your highest loaded areas, any kind of a crack there usually will propagate to cause failure. So a list of defects and their definitions are given in ASTM F788. That is for the fasteners, and nut inspection is covered in ASTM F812. There are very similar methods of inspection, so I'll cover primarily the ones here just for fasteners and leave the other part out. Now, quench cracks. Quench cracks are caused by excessively high thermal and transformation stresses during heat treatment. And so getting one of those means that you've got problems with the material, so you could have a problem with it. So in general, quench cracks of any detectable size by visual inspection make the fastener unacceptable. And here's another one. This is a pet peeve of mine. Socket head depth. Even though if you go to any of the ANSI specs and or mill specs, any of these on socket head fasteners, they give dimensions for the depth of socket. But I have yet to find anybody that's ever checked one We had a problem here a couple years ago with some NAS fasteners that the heads popped off of them in a wind tunnel installation, and when we looked at them, the socket depth was too deep. Well, you see, in a socket head, if that depth gets too deep, you wind up with a small annulus of area there is all you have left. If you get below the bottom of the head with the socket depth, you're in trouble, and that's what was happening. And although everybody talks about them, they're like UFOs, no evidence there. Here are some examples of the things in head and shank inspection. And cracks in general, these are quench cracks, which you can see can happen in the heads, in the shank, around the top of the head. But here's the one that really gets you. If you have any cracks here in this radius, fillet radius under the head, you're in real trouble. So that is from that FFS 86 or ASTM 788, I don't remember now which. Forging cracks. Now, remember I mentioned on fasteners that the higher strength ones usually have forged heads because you don't want to have the discontinuity in grain flow at particularly at the fillet radius. So you can get forging cracks during the cutoff or forging operation, or even cold forging. You can get some on the material if the material is a little bit too hard when you're cold forging it. And these are located on the top of the head or on the raised periphery around the indented head bolts and screws. And you can accept some of them if they are very, very slight, so that they're more or less a streak rather than a crack, just a indentation mark, as long as they have a very shallow depth. But once again, depends on the criticality of the installation as to how much you accept in the cracks. Here's one that shows a forging crack on the top of the head. And if you look at those limits on depths, you'll see that if you take 0.04 times the diameter or something like that, for a bolt that is, say, 1/4 inch in diameter, that's a pretty shallow crack. It's nothing more than a streak that you can see. So, so that type of crack, so-called crack, would be acceptable. Now here is a shear burst, and that's an open break in the metal from forming, and you can accept these only if it's in the flats and extends into the crown chamfer circle at the top of the head or in the underhead bearing circle, and none of them located at the intersection of the wrenching flats that reduces the width to cross corners below its specified minimum. In other words, you can accept some of these, once again, if they are so shallow that they don't look like a crack itself. But just beware of them, because this is one here, and you see this one amounts to just a little dent on the corner of the flat. So that would probably be acceptable as long as it did not look like a crack itself. Folds, that's a kind of a doubling over material which occurs during the forging operation and usually occurs near the intersection of diameter changes, particularly with non-circular heads. And the only problem that you look at with that is you can allow them in some cases at the corners, but you don't want any near the fillet radius of the fastener in this area here. Now here you're getting it because you're trying to form round cross-section into a square. So it's kind of hard to form that without getting some deformation and burrs around it. So once again, you look to see where it's at and evaluate it before you accept this on a fastener. Now, seams are usually in the raw material before forming, and they're pretty straight. And see, seams are acceptable because usually they're not a crack per se, and they're shallow and have a pretty good radius. Now, see here, if you look at this, it's 0.03 times the diameter. So if you go with a half-inch fastener, you see you still have something there that you would have trouble even seeing. It's so shallow. So that would be okay. Surface voids. You can get this in a material due to the way it's formed, but you got to watch if it indicates there's probably something wrong with the chemistry of the material if you're getting a lot of voids in the surface. And once again, the void depth, look at the amount here that you're allowed, 0.02 times the shank diameter. That's still, or 10 thousandths, all right, a 10 thousandths void is a pretty shallow one. And then this one I would look at if you had void areas that are that high a percentage of the underhead bearing area. I would look at the material to see whether I had the right material chemistry or not, and whether I'd want to reject it on that basis. Now, tool marks, nicks, and gouges, they're permitted on the underhead surface, but you notice the restriction on that. As long as your micro inch surface roughness does not go under the 125. Well, you see, a 125 is really not too rough. It's a rough machining surface. And so the other place that you would look at, if the head is banged up a little bit and it's on the corners out of the way, you could probably accept it, as long as the plating surface is not gouged. Now, plating inspection, this is another one of those that we talk about, and people don't do other than look at it and say, yeah, that's a gold color, so it means it's got chromate in it, and don't see that it's gouged up too much, so I guess it's all right. Most of the platings we've discussed earlier, but we didn't discuss anything on the inspection of them. So we'll kind of limit our coverage here to zinc and cadmium platings, except for just visually looking at the things. And the substitution of zinc for cadmium and using a dye to mask the color is a common way to cheat. It's done a lot, and because the chromate dye that you use usually, you look at it and the fastener is a gold type color, and you can't tell by looking at it whether it's zinc or cadmium. So the only way to find out is actually to run a test. Now, you can do two different things on it. You can destroy the plating on a fastener and take a chunk of the plating and go put it in a scanning electron microscope and see whether it's mostly cadmium or mostly zinc. But then there are other things that you can do here too than in inspecting. Now, zinc is usually covered by STM B633, and cadmium is covered by a federal spec QQP416. You can do process control inspection, and the plating outfits are supposed to do that, and most of them do, so that they control the amount of additives they put in. If their bath gets tired, they can add chemicals to it and so on, and take new readings, determine how it is plating. And you can do lot sampling inspection, visual inspection, and plating thickness tests. There is, in fact, I believe a guy from here at Lewis just recently developed a method of inspecting the thickness of plating. Dan Roth works over in the M&S, or what used to be M&S, I believe, developed one. But there are methods of looking at, and I think ultrasonically measuring plating thickness on materials. You can do an adhesion test, you can do a corrosion test, and you can do a hydrogen embrittlement test. Although the hydrogen embrittlement test, you can get that with both zinc and cadmium, so that in itself would not be conclusive. The lot sampling technique, you can take a lot of plated fasteners of the same metal composition and so on, and take a bunch of samples out, visually inspect them, look to see if the plating is smooth, and to see whether it adheres properly, whether it has blisters in it, pits, and that sort of thing. And then you can, you can measure them non-destructively by these various tests. There's an electronic test, eddy current, magnetic, beta radiation, backscatter, and all these things. That's covered in one of the sections of the Mill Handbook H28. You can take plated specimens for the required adhesion, corrosion, and hydrogen embrittlement tests from a production lot at scheduled times. You can determine the adhesion, and this is a real scientific method, by scraping the surface with a knife and then looking at it to see whether it is adhering properly with a magnifying glass. That's a method of inspection that you can do yourself. Now, corrosion resistance is determined, of course, by doing your salt spray test, which runs 96 hours. And after the exposure, the presence of corrosion products visible to the unaided eye at normal reading distance is cause for rejection, because you should not get any rusting on it or deposition of corrosion products for the 96 hours. Now, hydrogen embrittlement testing, this one is, there are different schools of thought on where you should start on the hydrogen embrittlement testing. Some of the fastener manufacturers of the lower strength fasteners say, gee, you don't have to do it on lower strength fasteners because you can't get hydrogen embrittlement. Well, a guy by the name of Lou Raymond, who is kind of the guru in the U.S. on hydrogen embrittlement, ran some tests and decided that you get hydrogen embrittlement all the way down to about a grade 5 fastener. The only thing is it takes it longer to show up. So in this ASTM spec, it only, they go anything above 144, which means your grade 8 would be the first one that you would test, and put it at, crank it up to 85% of tensile element for a minimum of 72 hours, and you shouldn't have heads popping off. If you have heads popping off, then you have hydrogen embrittlement. Now, the sample size and rejection criteria, normally you pick a bunch of random samples out of a bin and test them. And the ASTM F788 has a table, which we'll show later, that gives you the number of samples that you should take for a given production lot. Another one is given in this ANSI ASQC Z1.4, which superseded Mill Standard 105. And then we have ANSI Spec B1818.1 that gives some sampling techniques. The basis of all of these is to randomly pick a small sample, and any failure of the samples rejects the whole lot. Here is one from ASTM F788, which shows you the sample size that you should take for a given lot size. And you check it for all of these different tests that you want to run. And once again, the amount of testing that you do depends on the criticality of the design. So if you find that they're okay, you can proceed and accept the quantity of fasteners that you have. If you find problems, then you could go ahead and insist on more testing to verify that it's not as serious as it appears on the surface. Now, for macroscopic examination of products with seam indications, here is a sample table from ASTM F788. And you can take them a look at them according to this sampling technique, and if they are not judged acceptable, then you can either conduct more tests or reject the entire lot. There's been a lot of talk on the lot traceability and commingling and certifications and so on concerning the Fastener Quality Act, which is also known as Public Law 101 amended. It's 101-592 as amended by 104-113. And of course, one of the things that is covered in that law is lot traceability of fasteners. The customer can ask for the steel manufacturer's name, the lot number, chemical analysis of the wire from which the fasteners were made. And of course, from domestic suppliers, this information is readily available because most companies, when they make fasteners, they get a bill of lading with the coil material that gives all this information on it. But on imported fasteners, then it's a bit of a problem to get it because you have to get the certification from the person who made it in the foreign country. Now, on commingling, this is something that's kind of a new word, but what it is, in the past, the fastener distributors would get fasteners from all different suppliers, put them together in a barrel, and when someone ordered some, they'd get a bunch out of the barrel. So it would be theoretically possible for you to get 100 fasteners made by 25 or 30 different manufacturers. Under this part of the law, the commingling would be cut way down to where you can only have the fasteners from 2 different manufacturers in the same lot, because each manufacturer must register his trademark with ASME. Then he must stamp his trademark on all the fasteners covered by the law. Now, the minimum sizes covered are 1/4 inch in the inch system and 5 millimeter diameters in the metric. Of course, that is not altogether true, too, because if the fastener is through hardened, in other words, if it's a heat-treated fastener, then smaller sizes are covered, but nearly all of the small sizes are excluded from the law because they're not heat-treated that much. Now, if the fasteners haven't been exempted, they're now restricted by this commingling rule. And, of course, you can't have more than 2 lots in the same container. At least this way you have a better idea of who the manufacturer was on your lot of fasteners that you're getting for your usage. Customer can demand certifications such as the material lot numbers, chemical analysis reports, and tensile test data. And this documentation is notarized and legally binding on the supplier's part. Now, in the past, we could get certifications with fasteners, but they normally were a sheet that the clerk who filled the order initialed and said, these are certified to be good, and that was it. And so nobody was legally responsible. So if it is done this way with the certification, then the supplier is legally responsible for the fastener. So one of the gimmicks that some of the distributors are using is they're saying, okay, you want certified fasteners, it'll cost you 3 times as much for certified fasteners as uncertified fasteners. Now, do you really want certified fasteners? So that's one of the loopholes. If the distributor is not required to provide certifications, he's not responsible for fasteners anymore. The other thing that is in that law, which is a real big loophole, is agreement between customer and manufacturer. Now, if the customer is a clerk who knows nothing about fasteners, they can make all sorts of agreement with the manufacturer without even knowing it. So in other words, it's don't ask, don't tell type thing with these fastener certifications. If you don't ask for them and insist that you get them and pay the surcharge for getting them, you're not going to get them. So that's where the Fastener Quality Act stands, and although a lot of fastener manufacturers are scared and a lot of companies are scared on it, I don't honestly think myself that it's going to amount to that much in the long run. It is being handled by NIST, and of course the government will enforce the laws. How much they enforce them, nobody knows yet. I went to the school that they taught on how it would be implemented. It's something like a 100-page document. Even the lawyers can't agree on how it should be interpreted. So they'll probably ask for another delay in May of '98. Now, as far as inspection and test standards, there are all kinds of specifications for test and inspection methods, and what we have done is listed as many of those as we can in the appendices. We also have general references in the appendices for where some of this material came from and additional references in case you'd want to check further. Since so many fastener tests are done per Mill Standard 1312, we'll give a summary of its contents here, just kind of go over it. It establishes standard methods for testing fasteners in both the metric and the inch-pound system. And the standard test methods yield data and design allowables that are safe to use. In fact, Mill Handbook 5 uses Mill Standard 1312 for running their tests on both materials and fasteners that they publish in the book, and also fastener allowables in the joint section of Mill Handbook 5. Each test has a standard method spelled out, and there are book forms for each one of them, so that you have a dash number for it that gives you a standalone document, if you will. So if you turn over to the next page, here are the different categories: the salt spray test that we've covered, the interaction test, humidity, lap shear test, stress durability, hardness testing, tensile strength, stress corrosion, stress rupture, fatigue, the thickness of metallic coatings, and double shear testing. And then we go to torque tension, clamping forces for installed or installation formed fasteners, stress relaxation, elevated temperature tensile test, sealing, single shear, shear joint fatigue, receptacle push-out panel fasteners for electrical, tensile strength of panel fasteners, and receptacle torque-out fasteners. Then you have driving recessed torque for a quality conformance test, structural panel, lap shear, sheet pull-up. Now this is something that is important, and some of the cherry rivet type manufacturers, the pull stem type rivet manufacturers, have had trouble meeting the this sheet pull-up, because if you have several sheets together, maybe they're not exactly flat, and you try to pull them up and clench the rivet. Sometimes you have trouble passing this test with these pull stem rivets. So a lot of the manufacturers have had to go back and revise things to get a little more pull in the system so that they can lock the rivets. So that's what that one is used for. That one there would be for the blind fasteners. Then you have locking torque tests. And this last one here has been, I'm not sure whether the final copy of that one is even in the book yet, but I know at the last committee meeting we had, it was discussed that that one was being published. Barrel nut tension tests, which we didn't have, Dave, when we did the CM1 V-bands. Now, for the metric side, you have these that are covered, and they, for some reason or other, they changed it to a DOD standard 1312 for the metric in order to differentiate from the mill standard. And these are the ones that they have for testing of metric fasteners. Now we go into the do's and don'ts of fastener designs, and I've kind of come up with a set of guidelines here, just common sense type guidelines that for you to use, and it's not a complete list because you can always come up with an addition for a list. But these at least could be used as a designer's checklist. And one of the things that's a pet peeve of mine is I feel that enough information should be given on a drawing to fully define the fasteners you want. And I know in the past I've been disappointed in some of the drawings in which they say all fasteners to be per FFS 86 or 85. Now if you go look at that spec, you can get anything from alloy steel, stainless steel, down to even nylon fasteners on it. So you're giving the guy a lot of leeway if you don't define it any further than that. So this is why that I said fully define the fasteners you want. In other words, when you call them out for a specification, give the paragraph of that specification that covers the fasteners that you want to use. Or if you are not satisfied with how it's defined in the spec, give the strength level required. For example, on drawings, on materials, I know I have seen on drawings where it is critical enough that you even specify the grain direction on the drawing. Because, you know, on materials, you have a longitudinal, transverse, and short transverse directions on them. The short transverse is usually the weak one. So you specify on the drawing and the area of major stress that you want that to be the longitudinal direction in order to get better properties. So specify what you want on the face of the drawing. Now here I mentioned earlier in the course, use a nut that's softer than the bolt. That'll keep you out of trouble and that it distributes the loads on the thread, because usually if you torque a fastener to failure with a nut, it will fail in the first two threads in the thread runout area due to stress concentration. So the nut will not fail usually. It's the bolt that fails. And don't use feather edges on sheets in a joint. Match drill for countersunk holes. Use floating nut plates for critical designs, particularly for countersunk fasteners, so that the countersink can center the fastener and the nut plate will not be trying to bend it. Determine the environmental conditions before selecting materials or coatings for fasteners, because you want to make sure that you're covered with your temperature range. And design shear fasteners to be critical in bearing. That means that the fastener is stronger in shear than the material, so therefore you can elongate the hole in the material to allow your fasteners to pick up the load without failing the fastener. Don't use jam nuts for locking. Check alignment of fasteners before final assembly. And of course, as a corollary to that, avoid head bending, because the fastener bending, I think the SAE handbook says don't go more than plus or minus 2 degrees on misalignment on a fastener head to avoid trouble with bending. And follow the edge distance and spacing guidelines on fasteners. Now, you can temper this, but one of the things that you don't do is put a fastener so close to the edge that if the tolerance goes against you, when the hole is drilled, you'll have it pushing out on the edge. And I've seen some that were almost that bad. Now, don't use fasteners that look alike but are made of different materials. Don't use 300 stainless and A286 stainless, the same size, same head and everything, so that you can't tell the difference between them. And don't use fine and coarse threads in the same assembly unless there's a big difference in the fastener diameter, so it's not possible to get them in the wrong holes. And here's something that you can get in trouble with, although we did it on fittings on CM1. Don't mix metric and inch fasteners in a design. That'll get you in real trouble. Verify that you have the fasteners you specified, and demand traceability. If it is a critical design, make sure that you get the proper traceability of the fasteners. Use inserts in soft materials to avoid fastener pullout if you can't use through holes. If the dominant fastener load is shear, don't use a high torque on the fastener, because you have to combine the fastener and shear loads to the total strength of the material, so you don't want to use up all of it in tension if your primary load is shear. Avoid tapped holes as much as possible, because you can't inspect them. You're not sure how good they are, so if you can avoid them, don't use them. Use hardened washers under both the head and the nut on a bolted installation if possible. Don't torque a fastener above its yield point. Stay below the yield point, and don't get close to it unless you run sufficient tests to determine pretty much where it is. Then in a fatigue joint, if you have to go up because of fatigue, then you can go up to a near yield torque. The use of lubricants lowers the coefficient of friction, so the torque values have to be adjusted accordingly. One of the cases we had at the Cape of this, using silver-plated nuts, stainless steel nuts, of course the silver tarnishes, so if you have them in a barrel for a long time, they look bad. So some manufacturer decided he would stop that, so he coated these silver-plated nuts with wax to keep them from tarnishing. They didn't tarnish, but nobody told the guy using the torque wrench. So they were yielding these things all over the place and couldn't figure out why they were yielding until somebody found out that because the wax actually reduced the coefficient of friction to about half of what it would normally be. And torque tables are only guidelines. The design engineer should determine the torque values for his design, because that's why you don't blindly use a torque table. It'll get you in trouble sometimes. Fasteners loaded in fatigue should be torqued to near yield values. I mentioned that earlier. And before we go into the frequently asked questions for design, we'll take a short break and come back then and finish up the question and answer section.